All right, well, it's about 1 minute past. So let's get started. Today, we're very pleased to have Pawel Sobocinski talking to us about electrical circuits with string diagrams. Please, Pawel, the floor is yours.
Thank you, David. Thanks for the invitation. It's a pleasure to give my second talk at the Topos Institute. And it's actually pretty good timing too, because this talk appeared, I gave a very similar talk just recently at a workshop at NIST, and I noticed that David then repeated his talk that he gave at the Topos Institute that appeared on YouTube about 2 weeks ago. Because I want to reference that talk. I actually referenced his talk also at the workshop. So I really love that talk. I think it was a really beautiful account of, let's say, the methodology of ACT and what's one of the very promising ways that I think we can move forward and advance as a distinct field. And let me just summarize sort of my takeaways from that talk. That I think I agree with David that somehow the things that we study in applied category theory, things like compositionality, things like these sort of mathematical design patterns, so to speak, so these kinds of patterns that appear in several different places are very useful, and we have nice syntax. We often end up giving a much better treatment of corner cases. And I think we're developing, a lot of the sort of the research in ACT is about developing the mathematics of open systems. So I hope that you'll take away from this talk thinking that this is what I'm going to talk about as a nice example of this kind of thing. So what I'll talk about is a particular kind of relational algebra, right? So I'll talk about an algebra that allows us to talk about relations. The algebra itself comes with a diagrammatic syntax, so it's going to be a string diagrammatic syntax. And it's going to allow us to talk about things called linear and affine relations, and in particular affine relations are the things that are going to be very useful, as we'll see, for describing electrical circuits. And this kind of diagram here, you might have seen it before. I think it's been popularized in several of John Bars's works. The idea is that this really, this kind of captures one meaning of what we mean by compositionality, right? So we have some kind of category of syntax, some kind of category of semantics. So for me in this talk, these are symmetric monotal categories. And typically the thing on the left will be some kind of string diagrammatic like thing. So it's a syntactic thing. The thing on the right is a semantic thing. So maybe, again, linear relations, affine relations. And so each diagram denotes some kind of relation, and this mapping here is a functor, which basically means compositionality in this very similar sense to, let's say, how tasking semantics of first order logic is compositional, right? So the meaning of the compound phrase is obtained from the meanings of the components via the natural operation in the semantic universe. So the syntax is a close fit for the semantics. And then we might want to ask additional things of this mapping, right? So things like, we want it to be faithful. And faithful in this case would correspond to the property that logicians call completeness, right? So, so the fact that this is a functor already implies this property that logicians would call soundness. The fact that if we prove something that's equal in a syntactic thing, that will obtain equal semantic things. But if two things happen to be equal in the semantic world, and this functor is faithful, then that means we can already show that they're equal over here, right? So a faithful functor is something like a sound and complete reasoning system. And then one might even ask for something like fullness, and that would mean that every single semantic object has a syntactic description. So let me just say a little bit about what I mean by mathematics of open systems. So you might have seen, if you've ever studied any electrical engineering in your first year course, you might have seen diagrams such as this. So this is a bona fide open system, right? So we have some electrical elements here. We've got a battery, we've got some 3 resistors, we've got some junctions, and we've got these things called open terminals, right? So the idea is that we want to analyze the circuit in a larger context of perhaps other things. And what actually happens in sort of these first year electronics textbooks is that this diagram is not really treated with the full respect of mathematics, right? So this is some kind of thing that allows us to think, but at some point we have to throw away the diagram and translate it into a bunch of equations and maybe write down some matrices and do some linear algebra. And then, that's the serious mathematics, and then that gives us the answer, and then we can talk about what the circuit really means, right? So I don't like this. I think it ignores a lot of interesting corner cases. So again, coming back to what David said in his talk, and so therefore, and I think it hides a lot of the beauty of these kinds of systems. So I want the diagram above to be first-class syntax. So I really want this diagram here to be an arrow in a category, an arrow in a Monotal category, and we'll see in the second part of the talk exactly this. And then, of course, as I said in the previous slide, we want this. So we want a functor. We want to take these syntactic things, so these open electrical circuits, and map them to their meaning, which in this case there'll be a certain affine relation. And why is this a relation? Well, this thing here has 3 open terminals, right? So the idea is that this is not a functional relationship between the terminals. That it's not like the thing there on the left is an input and the open terminals on the right are outputs in any sense. But this thing describes some relational behavior in the sense that there are some observations we can make about these 3 ports, these 3 open ports, which characterize the legal behaviors of the circuit. And that's a relational thing. And it turns out that this is compatible then with how these circuits will compose too. So that's essentially where we want to get to, and that's going to be the end point of the story. So I want to start with a really brief introduction to string diagrams, the way I like to think about them. I'll tell you a little bit, an interlude about sort of doing universal algebra string diagrams, and this ties into the first talk I gave at the Topos Institute, but I won't say very much about it. I'll just say enough to give you an idea of what kind of theories are these theories that I'll talk about in the second part of the talk, so graphical linear algebra and sort of graphical affine algebra and electrical circuits. Okay, so let me start with my story of string diagrams. So I like to think of string diagrams as syntax, right? So therefore, I like to present them the way computer scientists present syntax. And computer scientists present syntax typically by some kind of recursive syntax definition. So something like Backus-Naur form definition, right? And it's not very difficult to do this for string diagrams, right? So I'm interested in some kind of Monotal signature, right? So these are my basic operations with which I'm going to construct my string diagrams. So an operation gamma has an arity and a coarity. So you can think of this thing as some kind of, number of inputs or number of outputs. Inputs and outputs are dangerous words. We don't want to immediately assign causal meaning to these things, but essentially that's an okay thing for you to think of for now. So we have an arity and a coarity, and then we have a term syntax, right? So what's a term? I can have one of my elements of a signature. I can have something called epsilon, which I want to think of this as the identity arrow on the Monotal unit. So this is going to be like the empty diagram. The identity arrow on one, so this is kind of like a while, a twist. I have composition, and I have tensor product. Now, there is one slight caveat here. Of course, the syntax will allow you to write terms that are not well typed, in the sense that, of course, we know that composition has to respect domains and codomains, but this is a very minor technical point which can be handled with something like a sorting discipline. It's really not a big deal. Okay, so I can write these terms. This is like a real syntax, but it's not a very nice syntax, right? It's an old-fashioned syntax. I'm producing these syntax trees, and these syntax trees do not capture, of course, all of the equations of monotal categories. These syntax trees then have to be quotiented by these equations. Now, fortunately, we have string diagrams which do all the quotienting for us, right? So let me introduce the diagrammatic convention. So for my operation gamma, I'm just going to draw this as a box with the arity number of y's on the left, co-arity number of y's on the right. My identity on the monotal unit is just an empty diagram. This is my syntax of the empty diagram. Identity is just a wire. The twist is the twist. Composing is just plugging wires together, and tensor is stacking boxes, stacking things. Okay, so this is so I give you, using this diagrammatic convention and using the recursive structure and terms, I can basically draw you a diagram for any term, right? Or any well-typed term, but as I said, this is a small technicality. But of course, then you're going to draw diagrams that look very similar to other diagrams that are obtained from not equal terms, right? So for example, to disambiguate terms, we would need to add additional sort of dotted boxes that tell us which way the brackets go in a term. Okay, so here we have a different kind of bracketing. So these are different terms, but they end up giving us diagrams that look the same unless we reintroduce some additional kind of information to diagrams. And sometimes it happens that different terms lead to diagrams with the same connectivity, right? So for example, if I just start with some M, let's say this is a generator, and I compose the identity Y, then I get something with a slightly longer Y on the right. But let's say the connectivity of these two diagrams are the same. So the good news is that we don't want any of these additional dotted boxes. We don't want to distinguish terms with the same connectivity, because there's this fundamental theorem that says that two diagrams obtained from terms C prime have the same connectivity if and only if they're equal in the theory of symmetric strict monotal categories. Okay, so a string diagram is a class of diagrams obtained from a term up to this idea of only connectivity matters. Of course, I'm not being 100% formal, but I think you all get what I mean. So the string diagrams, given that this is the case, the string diagrams are the arrows of the free symmetric strict monotal category on gamma. And the objects of this thing, of this animal, are natural numbers. These kind of keep track of the dangling wires and arrows of string diagrams. Okay, so in this way, you'll see that the way I introduced string diagrams, okay, was very fast. It wasn't particularly precise, but what I like about this kind of introduction is that it really emphasizes the syntactic nature of these things. I really want to think of these things as syntax, and they are syntax, right? So they are free. They are free on something. And so the usual things that you do in computer science on syntax, so for example, inductive definitions, etc., and using recursion, all of these things are available to us when we use string diagrams. They're very pleasant generalization of, let's say, what is the notion of a classical term. And I want to give you an example of this in action now, sort of leading up to the second part of the talk. Which is, I want to give you some idea of the relationship between doing algebra with string diagrams and, let's say, doing traditional 20th century algebra. So to do that, I'm going to talk about symmetric monotal theories. So a presentation of a symmetric monotal theory is a pair gamma E, where gamma is the monotal signature. So these are things we've already seen, just a bunch of operations. And then E is a set of pairs of string diagrams of equal types, and these are going to give us our equations. Okay, just like a classical algebraic theory is a set of operations with an arity and a set of pairs of terms, which are the equations. So here's a little example: the symmetric monoidal theory, or I should be careful and say a presentation of the symmetric monoidal theory of commutative comonoids. So I've got a co-multiplication here, something where with arity 1 and co-arity 2. a co-unit, something with arity 1, co-arity 0. And then I've got 3 pairs of string diagrams, which encodes the equations that I want this theory to satisfy. And so these equations tell me in order that the co-multiplication is commutative, it's associative, and it's unital. Okay, so given such a presentation, I can generate a symmetric monotal category from this data, right? So what does it look like? Well, essentially, I generate the free thing on the signature. So I just look at the string diagrams, and then I just take the string diagrams modulo diagrammatic reasoning according to these equations. So if you want, this is a set which is quotiented by the smallest congruent that contains these equations. But it has a very natural feel. I mean, it's just what we're used to in sort of, let's say, universal algebra, right? So it's terms modulo equational reasoning in the particular algebraic universe you're in. And we can start making some connections between, so this is a very beautiful theorem I want to talk to you about that makes it's due to Fox from 1976, that makes a connection between what is a Cartesian category, so that's a category of finite products, and categories in which objects are equipped with a commutative comonoid structure. So why is this important? Well, somehow Cartesian categories were identified by Lauvier as being fundamental to the study of classical algebraic theories, right? So as you know, most of you have probably heard of, Lauvier's approach to universal algebra, and there really somehow the crux of the matter is that a theory is equated with a Cartesian category, and then models of this are Cartesian functors from this category, okay, to some semantic universe, perhaps the category of sets. Okay, so what did Fox prove? Fox proved that Cartesian categories are those symmetric monotal categories where every object has a commutative comonoid structure. So, and in this talk, we're going to concentrate on a single sorted case. So like there's only one object, essentially, right? Every object is a tensor product of this object. So there's kind of like a generating arrow, generating type, and this guy has a commutative comonoid structure. And moreover, everything commutes with the structure, right? So every diagram has to be natural with respect to the co-multiplication and natural with respect to the co-units. So this is a beautiful theorem because on the one hand, the definition of a Cartesian category is something that talks about the existence of universal property, right? So it talks about the universal property of product, which is some kind of a global thing. You have to look at the entire universe, right? Whereas this algebraic presentation kind of feels quite local, right? I just know that locally I have this comonoid available, and I know that anything that hits me will be natural with respect to it, right? So it's kind of like a local global thing. That's the way I like to think about it. Okay, so what this seems to say is that if I take something like a classical algebraic theory, which is a Cartesian category according to Lauvier, then I should be able to understand it by looking at string diagrams in which, in particular, I have this chosen special commutative comonoid structure. Right? And that really is the case. And what this commutative comonoid structure does is it sort of does the variable management for you. So the classical variable, the way variables are handled in classical terms is precisely going to be handled by this comonoid structure. And I'll give you just some examples, just to give you like a feel for how one translates between, what we all know, this is the way we're taught mathematics, classical terms, and string diagrams. Okay, so consider the theory of magmas. So we have just one binary operation M, no equations, just to keep things super simple. And let's consider some terms in this theory, right? So we have a term mxy, let's say in a universe in which I have x, y, and z available as variables. Okay, so this forces you to be a little bit more careful about, let's say, your universe of variables that are the free variables in scope, which is, again, one of these kind of nice things about string diagrams. I think it forces you to What's nice thing about applied category theory, again, it forces you to be a little bit more clear about your corner cases. So what is this? Well, it's mx, the term is mxy, so I plug in, so the idea is that these three wires correspond to the variables x, y, and z. The first two are plugged into m, that's the output. And the third variable is not used, so it's just forgotten. Okay, so this is where the co-unit of my chosen comonoid structure comes into play. And you can see some more examples. Maybe this one is interesting here. You see that here we have a term in which x appears twice. And so this is where we explicitly use the commultiplication, and we kind of copy the x and then wire it up in the right places. Okay, so indeed one can essentially have an approach to classical universal algebra completely with string diagrams, because a Lovi theory is just the same thing as a Cartesian prop, right? So it's one of these. So a single sorted Lovi theory is a single sorted Cartesian prop. I mean, there's always, you can do the multi-sorted version or even sort of the unsorted version in this kind of setting, but I typically stick to the one sorted version just to keep things simple. Okay, so how can I see a Lovi theory as a prop? Well, we need this commutative comonoid structure. We need to make all our generators commute with it. And then I might add my other equations, right? So for example, let's say in the theory of groups, we might want to have an equation like x times x inverse is the identity. Okay, so let's say that we've chosen to represent the times here as the white circle, and the unit here as the unit kind of for the structure. Then this equation actually has x appearing twice, so this variable x has to be explicitly copied here, and then this inverse operation, which is denoted by the red box here, is applied. Okay, so this equation actually makes use of this Cartesian structure, this commutative comonoid structure that we have around. Now, what's the advantage of taking this point of view? Well, it turns out that sort of Fox's theorem is not the only such result, right? So we can change this sort of algebraic structure. So we now going to replace commutative comonoids with something else and obtain a very similar, kind of universal algebraic story. So one can essentially tell the story for the thing that we've called partial theory. So this is joint work with Ivan Di Liberti, Fosco Lorgia, and Chad Nestor. We had a paper last year at Pawel. So we call these partial theories. These have been called various things in literature. They're called quasi-algebraic theories. So quasi-variety, the idea is that the varieties here are quasi-varieties. Essentially algebraic theories is another thing that have been called, I think, by Freud. So these are essentially, the idea is that these are like classical algebraic theories, but operations are allowed to be partially defined. So it turns out that the right mathematical structure is, I'm not going to get into details, but I'll tell you the punchline. The punchline is you replace the idea of a Cartesian category with something called the discrete Cartesian restriction category. Okay, and again, a discrete Cartesian restriction category is something defined with universal properties, but it has again, like a Fox theorem, where the local structure is something we call a partial Frobenius structure. So we still have a commutative comonoid, but we also have kind of a multiplication structure without a unit. Okay, and it turns out that this multiplication together with the co-multiplication satisfy the laws of special Frobenius algebras, but kind of the unit is not there. So we have so my object has this algebraic structure. And by the way, you can think again of the copying and the discard as you did before. Now this monoid structure, this multiplication structure, this is like a partial equality check, if you want an intuition for this. And it turns out that, okay, before we had to make all our generators commute with all the structure, here we only need to commute with the co-multiplication and then add my other equations. And this allows you to have this string diagrammatic approach to this class of partial theories. Again, you can play the same game, generalizing further. Oh, by the way, here I should say one more thing. So in the classical case, let's say the paradigmatic universe for models is the category of sets and functions, which is a Cartesian category. So here, the paradigmatic category for the semantic universe is the category of sets and partial functions, which is a discrete Cartesian restriction category. And one can play the game also for, let's say, even more permissive theories, which we call relational theories. So here we use something called this is due to Carboni and Walters, this notion of Cartesian bicategories of relations. Again, I don't want to go into details, but again, there's kind of like a Fox theorem for these things, and there's a recipe for building these things up. And here we want to consider models as functors to REL, and REL is a Cartesian Cartesian bicategory of relations. So by generalizing this classical notion of what is syntax and considering string diagrams and syntax, we have this quite smooth, I think, generalization that allows us to go from classical universal algebra to these essentially algebraic theories, partial theories, quasi-varieties, whatever you want to call them, to things even more permissive, something that really talks about relational structure. And we have variety theorems for both of these things. So the varieties for partial theories are just locally finitely presentable categories, which I suppose is probably not that surprising if you know about essentially algebraic theories. The interesting thing is we also have a variety theorem for these relational theories. And one of my PhD students, Chad Nesta, is writing a thesis about this, and hopefully this will be complete around this time next year. Okay, so I think I'm okay for time. It's only past, so I've gone through the first half of my talk. And so now I'm going to talk to you about two particular concrete examples of relational theories. Okay, so first I want to talk to you about graphical linear algebra, which is a relational theory of linear relations. And then I want to talk to you about affine algebra, which is the theory of affine relations, and how then we can use that as a nice calculus to reason about sort of electrical circuits with open terminals. Okay, so what's happening on the slide? So we want to get into things that feel like universal algebra. So by the way, a few slides ago, okay, I've been kind of flashing slides, but what is the Liouville theory of commutative monoids considered as a prop, right? So, well, I need to give myself some signature for my monoid. So that's the stuff I'll denote with white here. So the white multiplication, white unit. But we know we have to have, in order to consider this as a prop, we know we have to have a Cartesian structure. So we have this canonical co-multiplication, the co-unit. And we know that this white structure has to be natural with respect to the black structure, and that yields all these equations. Okay, so this is the same thing. So the Liouville theory of commutative monoids is the same thing as the symmetric monotal theory of commutative bialgebra. Okay, you might recognize these equations as being those of commutative bialgebras. But there's yet another way, kind of like a syntactic sugar for these for arrows of this thing. And these are just matrices of natural numbers. So this is kind of the first hint of some kind of linear algebra coming in. And why is this? Well, first of all, I can just give myself a sugar for natural numbers, right? So I'm going to just say that the co-unit followed by the unit is 0. And then I'm going to say that k plus 1 is k with this additional path followed by the co-multiplication followed by a multiplication. Okay, so this is, in a sense, what this syntactic sugar does is it counts the number of paths from left to right in the diagram, and then in a one-to-one diagram. And now you can start using kind of your programming language intuitions about, you know, syntax being an inductively defined thing, and start defining lots of things recursively. And you can, so because this is, you know, this is a recursive definition, an inductive definition, so we can prove things by induction. So in particular, we can prove that, you know, for example, this lemma that if I, m paths and n paths is just the same thing as m plus n paths, etc. So you can start sort of doing inductive proofs about basic arithmetic. And if you now consider diagrams with more than one y on the left and one y on the right, well, it turns out that these are precisely in one-to-one correspondence with matrices over the natural numbers. And the way to see that is you think of the entry in the ith row and the jth column as the path from the jth input to the ith output. Okay, so here, for example, we are in the first column, so we are looking at the first input, second row, second output, and this is a 3, so there should be exactly 3 paths. Yeah, and so this is the correspondence. Okay, so this is the starting point, and this is kind of like the basic building block of the theory of linear relations. But first, I want to before I tell you what the presentation is, if you haven't seen it already, let me just tell you about the semantic universe, just so that we're on the same page. If I give you a vector space K, then rel K is the symmetrical monotal category where objects are natural numbers, and arrows M to N are relations essentially from K to the M to K to the N that are also K linear subspaces, right? So they're also closed under addition and scale multiplication. So what is graphical linear algebra? Well, it's going to be a presentation of the relational theory of linear relations. So this is exactly coming back to the slide we had at the start. We're going to have a functor from, we're going to consider functors from a particular symmetric monotal theory. So this symmetric monotal theory of graphical linear algebra to rel, and that's going to pick out all of the different categories of linear relation, categories of linear relations for different fields. And in fact, the free model is isomorphic to the symmetric monotal category linear LQ. Okay, so somehow the free linear relation is the linear over the rationals. So in particular, this means that for this particular kind of semantic universe, if we're interested in linear LQ, this is somewhere where the syntax, the string diagrammatic syntax, is sound complete, but also fully complete, right? So it's the functor is as an isomorphism, so in particular it's full and faithful. So that means every linear relation over the rationals has a corresponding string diagram that maps to it. Okay, so I'm going to give a really brief summary of what's going on in this symmetric monotal theory. So we have here sort of in the bottom row we have the generators of a bialgebra, and now let us imagine that we also have kind of another bialgebra which goes the other way, right? So we're just going to turn all the generators in the mirror. So now we're going to have a black co-multiplication, a black multiplication, a white multiplication, and white co-multiplication. As relations, they're going to be the things that as relations, sort of the black stuff is going to be the diagonal relation and the addition relation. So this is just the relation of addition and the zero. This is thing that picks out the zero. And the opposite guys are going to just be the mirrored versions of these. Okay, but let me just outline the equational stuff. Okay, so everything is a commutative monoid and commutative comonoids. Whenever white meets black, they behave like bialgebra. Whenever white meets white and black meets black, they behave like a special Frobenius algebra. Well, an extra, because we also have the bone, also an extra special Frobenius algebra. Okay, so we have this, there's lots of equations, but actually everything is supersymmetric, right? So black and white are totally symmetric. And all these equations can be really summarized on one slide like this, apart from one final bit. And this is where this additional syntactic sugar that we introduced a few slides back comes into play. So we have the forward syntactic sugar using the black co-multiplication and white multiplication, but we also now have the backwards one where if you turn around. And this is essentially telling us that whenever P is not equal to 0, then P is invertible. This puts in the invertibility into the theory. Okay, so this is a symmetric monotal theory, and as I said, this is the symmetric monotal theory whose models in REL are precisely linear relations over various fields. And in particular, when I take when I examine the symmetric monotal category, which is obtained by just taking this, so I take my string diagrams and I take the modulo the equations. Well, it turns out that this is isomorphic to the prop of linear relations over the rational numbers. A very strong correspondence. So I said this a little bit before, where the generators go, this just gives you a little bit of an intuition, like kind of operational intuition, I guess, for what these things denote. So this is kind of really like the diagonal relation, the thing that copies, this is the thing that really forgets, this is the thing that adds, and this is the thing that's 0. Now, the interesting thing I think that this presentation shows you is that what is linear algebra? Well, linear algebra is not the definition of a field followed by a definition of vectors and matrices and bases and whatever. Linear algebra can be understood as the study of how these four relations interact together. Well, these four, if I want to be super, well, I guess, no, in fact, I think I would, yeah, I mean, it's because the opposites can be kind of obtained by, already by, with the structure, right? I already have a compact closed structure here, so it's really, linear algebra is all about these four relations and the beautiful ways in which they interact. So I quite like the slogan. Just to say a little bit more, the black and white satisfy exactly the same equation in the equational theory. So every proof is in fact a proof of two theorems in both the colors. Every fact is still a fact when viewed in the mirror. So there's also this left-right symmetry. And by the way, this is this kind of color symmetry is another interesting thing about, let's say, demonstrates a historical artifact of linear algebra. That typically, when we teach undergraduates linear algebra, we teach them with this kind of bias of bases, right? So we teach students that, let's say, calculate the basis of the kernel of this matrix or something. But there's a completely there's another way of doing this, which is has exactly the same expressive power. Instead of bases are vectors generating spaces. You can think of equations, homogeneous equations, of which we find solutions. Okay, so it turns out that this is really what this color symmetry here says. I don't know if I really should get into this. This is just some kind of a tutorial of basic linear algebraic concepts of string diagrams. I don't think I really want to get into this. And in fact, yeah, I've got some kind of fun string diagrams for just understanding what's going on. So things like fraction arithmetic, and things like dividing by 0, which again, I think maybe I'll say a little bit about this because I want to come back to this, right? So, so the cute thing about these diagrams is that they allow us to write down all the fractions, but they're not clever enough to stop us from writing something like 1 divided by 0, because they're just string diagrams, right? We can just write it, and it seems to be compatible with semantics. So what's going on? Well, it turns out that it's perfectly okay to divide by 0 in this particular case, and it's actually meaningful, right? So if I want to look at the entire algebra of one-to-one diagrams, well, I have all the fractions, I have 0, and I have these 3 additional elements. And if you want to get an intuition for what this means, is you have to think of projective arithmetic. So you remember projective arithmetic, we think about sort of numbers which correspond to sort of lines through the origin in a plane. Okay, so the idea is that each fraction is a line of that tangent as a fraction. So this gives us sort of one-to-one correspondence between sort of the rational numbers and lines, except for the vertical line, which we take to be this line at infinity. But it turns out that all of these lines are just one-dimensional subspaces of k squared, right? So why not? And multiplication corresponds to composition of these things as relations. Reciprocal turns out to be just relational, the opposite relation. But now, if we're just going to close this thing and consider it as a closed system, then we need to consider all of the linear subspaces of k squared. So in addition to all of the one-dimensional spaces, there's a single zero-dimensional space, which is the point at 0, which is this guy, which I denote by bottom, and the entire thing, so the entire two-dimensional plane, which is the thing that I denote by top. And then you can sort of write down a consistent multiplication addition schema. And everything is okay. And so I think this, again, like if I was going to talk about sort of like the traditional panic about dividing by 0, I think again a lot of this is sociological, because the fraction notation is just not a very good notation, because it encourages people to write something like 0 divided by 0, which is actually ambiguous, because in graphical linear algebra there's two different diagrams that are 0 divided by 0, one where the 0 sort of points into itself, and one where the 0 points out. And these things need to be distinguished, otherwise everything collapses.
Sorry, Pawel, can you say quickly what those dashes in the upper table mean?
Oh, they just mean that everything's commutative. So
gotcha.
So I think I just didn't want to repeat redundant information. Whereas, yeah, you have to be more careful with multiplication, because multiplication is no longer commutative on these additional elements. So addition is always commutative, but multiplication is not. That's why this table upstairs is symmetric, but the table downstairs is not. And you might think, that this is some kind of wow, big deal. It's just some kind of a curiosity that actually is just never really comes into use. But I'll tell you where it comes into use in the real life setting just in a few slides. Okay, so that leaves me about 7 to 10 minutes for the last part, which is okay, because I want to, I'm going to just make a very small extension to linear algebra, to graphical linear algebra, to cover affine relations. And then I'll tell you about how these affine relations can be used as a calculus for electrical circuits. Okay, so what's an affine relation? So this is a slightly weird looking definition. I don't want to waste too much time, so I'll just define it as it is. Okay, so it's a set which is either empty or it's a linear relation that's being shifted by a vector. So affine relations are closed on the composition. Okay, so the interesting thing here is that we have this new, like the empty relation is an affine relation, but it's not a linear relation. So F rel K is the subprop of rel, where R is affine relations, and everything's okay, everything composes, etc. So we're going to get we want a diagrammatic syntax for those, just as we had for linear relations. So what we do is we extend the syntax with another generator, which it's kind of just like this unit for the addition produced as a 0. Here we're going to produce the multiplicative identity. And you might think, okay, well, I've introduced this guy, and this guy is going to interact in all kinds of horrible ways with the other generators. Well, the good news is that actually there's only 3 additional equations. So the additional equations, the first 2 here, so Jupe and Del, they tell us essentially that this guy that we introduced is a is a nullary function. So it's a constant, right? So it commutes with so there's this equation says there's at most one of them, and this says there's at least one of them, right? So it basically tells you there's a single multiplicative unit, so to speak. And what this equation tells you, this is really where all the action happens. And this is something which takes into account the fact that now we have this empty relation around. And this empty relation, when you think about the empty relation, composing anything with the empty relation results in the empty relation, and also tensoring anything. So tensor here is just product. So tensoring anything with the empty relation is the empty relation. So empty relation is like this kind of nuclear bomb that just blows everything up. And this is like the nuclear bomb equation, right? So what does it tell us? It tells us that if we assert that 1 is equal to 0, so this is like the prototypical example of how we can obtain the empty relation, right? We can compose the thing that says star 0 with the thing that says 1 star. And that's the empty relation, right? So 1 is not equal to 0. So this is like some kind of false, if you like. So if I have false, then I can break wires. And that turns out to be sufficient, right? So that equation turns out to be sufficient for my equational theory. And we get the fact that you know, this is now a diagrammatic syntax for affine relations. So that was a paper, that was joint work with Filippo Bonchi, Robin Piedeleu, and Fabio Zanasi. And we had already in that paper developed this application to electrical circuits, which was heavily inspired by the work of John Byers and also the PhD thesis of Brendan Coyer. But actually, this kind of brings me to the last point that I wanted to make, which again fits into what David was talking about in his work, and this led to this paper with Guillaume Boisseau, which I'm extremely proud of. I think it's really wonderful work. It's mostly Guillaume's work. Guillaume basically came to me asking at some point for an open problem. I told him, well, we have this paper about you know, affine relations and diagrammatic syntax, and in it we have this case study of electrical circuits. Wouldn't it be cool? Okay, so in theory we have this calculus which is sound and complete and we can do anything with. Wouldn't it be cool if we took like an electrical circuits textbook, like a classical textbook, and just reproved all the theorems properly using string diagrams, right? And got rid of all the hand waving, got rid of all the dodgy translations into linear algebra, which are not always completely one-to-one and sometimes miss out on corner cases. And essentially Guillaume did this. He went away and proved the large majority of theorems in one of these textbooks. But what he did is in order to do this, right, so we know that string diagrams get big, right? So we need some additional calculational tricks. We need some additional syntactic sugar. We need some beautiful syntactic methods to deal with syntax, right? And this is something that computer scientists are quite used to, but mathematicians are not, right? So it's difficult to sort of convince mathematicians that this is a useful thing, even though I think for computer scientists, this is somehow part of the course, that sort of having cute ways to calculate is extremely important. And this is what Guillaume did. He introduced this thing called the impedance calculus. And this appears in this paper, which we have together jointly at ACT last year. And the idea is that using this impedance calculus, you can really prove classical theorems of electrical circuit theory in an elegant way. So I'm kind of running out of time, so I'm not going to get into details, but let me just get back all the way to the start of the talk, where I promised you that I want to think about electrical circuits with open terminals as syntax. Okay, so let me now deliver on that promise. So I'm going to give myself a signature with all of the electrical circuit elements parameterized by elements of the field, together with some basic sort of branching and capping capability, right? So we want to build circuits. And these are the usual elements. Let's not get into details because we don't have the time. Now, it turns out that all of these elements have a semantics as an affine relation. Now, this deserves a couple of words because it's a kind of an interesting functor from this. This is just pure syntax, right? This is this electrical circuit. This is GAA. And we map one to two. So we map a single wire to two wires because the idea is that each electrical wire somehow carries on it two values. It carries the voltage and the current. And these are the this is exactly what these wires here are representing. So the top wire is always talking about the voltage and the bottom wire is talking about the current. And then each of these electrical elements represents a particular affine relation. And the fact that so the point where we go beyond linearity is the fact that we can allow voltage and current sources, and this is where you see this additional element that we have now around this one generator pop its head. Okay, so we have this way of translating circuits into string diagrams of graphical affine algebra, which kind of gives the intended meaning as affine relations. And this is where the genius, I think, idea of Guillaume came. So instead of just doing this translation, instead of taking an electrical circuit and generating a massive string diagram, what we do is we introduce this technology called an impedance box, which will allow us essentially, once we sort of develop it sufficiently to a sufficiently advanced level, to kind of compile little bits of the electrical circuit and reason about it locally, and then recompile it back to the electrical circuits, right? So basically if I just introduce this kind of gadget into my syntax of eCirc, so this is like a little electrical circuit, which inside of it is allowed to have a string diagram of graphical affine algebra, a one-to-one diagram. And then its meaning is this diagram here. Then all of these elements, all of these circuit elements can have a kind of a unified representation as an impedance box. And it turns out that you can then prove lemmas about impedances in general, which allows us to derive things like inductors, resistors, and capacitors are directionless, whereas voltage and current sources flips polarities. It allows us to prove things like, the basic resistor formulas, putting resistors in series and parallel. It allows us to, and this is where I wanted to come back to the case of dividing by zero, right? So the formula we get for the sort of R1 and parallel of R2 is this diagram of graphical linear algebra, which, if we assume that R1 and R2 are not equal to zero, we can transform into the usual formula, which one can, for example, take as R1, R2 divided by R1 plus R2. But of course, all of these formulas in classical syntax fail when R1 is equal to R2 is equal to zero. But if R1 and R2 is equal to zero, then this should just be an open wire. It should just be a wire, right? So this is not something pathological to try and think about. Whereas in fact, this is what happens when we let R1 and R2 equal to zero. Then it's just a trivial proof, a simple proof in the syntax in the algebra of graphical affine algebra that this is sort of this backward zero, so this infinity thing. But when we plug it into the formula, we just get back the wire, right? So if you imagine the black co-unit here and the white unit here, you just get the two wires. Okay, so this is like an example where this dividing by zero really comes into play and actually derives something meaningful, right? Which I find cute. But anyway, look, I'm severely out of time, so let me just summarize here. Well, the point is that we can improve this technology of impedance boxes to allow things like string diagrams escaping impedance boxes, allowing us to define additional elements like voltmeters, ammeters, control voltage sources, control current sources, and then kind of really opened up closed circuits and start measuring things, right? Which is what introductory textbooks in electrical circuit theory make you do. So here we have some kind of a closed circuit with a battery which has let's say a variable voltage, and we want to measure the current depending on some fixed resistor, and we get a formula for this just by applying the calculus. The really cool part is that you can then really start proving these theorems of classical circuit theory, like relativity potential, conservation of current, which then, drawn in a string diagrammatic way, really capture, I think, the symmetries involved here. Things like independent measurement theorem, superposition theorem, things like the Venn theorem, etc. But again, I'm out of time, so I don't have the time to get into details of these. So thank you very much. Thanks for your attention. It's been fun to give this talk.
Thanks, Pawel. Okay, so people can raise their hands or just unmute themselves. Do you have a question? Bunch of clap emojis. Can you say
okay,
why?
no questions is also okay, right? Because for me it's 5 to 8 p.m. and I'm quite happy to take questions offline, right? So just Google my name and email me if you're interested. If you don't have any questions.
I have a quick question. Can you go back to the first impedance box slide?
Yes.
Yeah, well, a little past.
This one here?
Yeah. I'm really interested in something that was in this slide and the last slide, which is the I symbol and why it has. So it seems like it's saying that, if I'm reading it right, it's saying like you're forcing the thing on the left to be 1 over I, and you're allowing the thing on the right to be anything.
Yeah, so this is a current source, right? So the current source, it's exactly that. It's saying that the current source at the output has to be I.
Has to be I, right? Mm-hmm.
It's just that it's I going from right to left, right? So this is where the direction here on the I is. Whereas the current on the right can be anything.
Okay. Cool. It looks by the symbol on the left, like it looks on the symbol like on the left from.
No. Sorry. But this is in the impedance box, right? So this is
right.
But you have to then then you have to understand what it means when you actually compile it.
Mm-hmm.
So now
but on the previous slide it showed that.
There.
On the previous slide it showed that better, maybe. But I was confused about.
I think here, like, imagine what happens when I take what's inside this box and I plug it in as C.
Yeah.
Okay, what it then says is that the current is constantly I on the current wire. Okay, and the voltage can be the voltage difference, the potential difference can be anything.
Mm-hmm. Right.
So yeah, you have to be careful between, so for example, the identity wire has this impedance. It says basically impedance 0.
Mm-hmm. Wait, so are you saying?
Yeah, you have to. It's confusing, right? Because here we have a string diagram that lives kind of inside a circuit, but its meaning you always have to take into account that its meaning is something like this, right? It plugs into a co-multiplication followed by a multiplication up here.
So a blue wire is actually 2 wires, right? And one is representing current, and one is representing voltage. And they're both just numbers. So in terms of the relational affine calculus, I can't distinguish them as wires. But if they're bluified, then I know one's voltage and one's current. But once you see them in just the top thing, they're just numbers, right? They're like a wire is just, it doesn't differentiate between a current wire and a voltage wire. That's us doing
Yes, indeed. And that can get you, and then you can really start having fun with this once you allow your diagrams to go wild. Once you start having these controlled sources, right? You can take the current measurement from one and plug it into a controlled voltage source of another, and etc. So you can really muck around with types.
Does that have a real
again? I'm not a professional engineer, but I understand that this is something that is allowed.
Wow.
And that this can happen.
Wow, cool. Looks like we have one more question from Valeria.
Oh, hi, Pawel. Very interesting.
Hi.
Thank you. I'm not talking about impedance boxes at all. I want you to go back to the beginning of the story. Yeah, I know nothing about those.
I always feel quite embarrassed about this because Guillaume was the real genius here. So I'm talking about his work, and he understands this at a much deeper level than me.
Well,
so yes, I'm happy to go back.
But back to the Fox theorem. That's
yes.
And the generalizations that you're describing. One of the things that kind of caught my attention is this business that the way we're dealing with this stuff, we don't have implications, right? So because everything that you're talking about, I can think of them more logically. And then, if I have a Cartesian category, then I have simply type lambda calculus. If I have a monoidal category, I have some sort of linear logic calculus. And then the question is, have you thought of kind of improving or proving another extension of Fox's theorem that deals more with the monoidal closed category? So
yeah, that's an excellent question. I haven't, but there is an interesting thing to say about, let's say, Horn theories, right? So Horn theories have, so one way of dealing with these kind of partial masses, like if you look at, let's say, sort of quasi-algebraic theories and quasi-varieties. So a classical way of doing this is, instead of equations, you allow yourself Horn formulas, right? So you have a whole bunch of things that have to hold, and then you can derive an equality.
Right.
So it turns out that, and I've never written this up, and I'm writing this up actually now because I'm finally getting around to producing a journal paper of this work, that just as I had this kind of a translation between classical terms and string diagrams in the presence of this Fox structure, let's say, of this comonoid structure. Well, it turns out that string diagrams in the presence of this partial Frobenius algebra, you have equations between them. Well, the expressive power is exactly the same as these Horn formulas. And it's got to do with this this partial equality operator, right? So this partial equality operator, essentially, if you can always take a diagram in this theory and put it in this kind of a normal form that ends up looking like a Horn formula. So it's an interesting. It's like I always love these sort of getting some intuition for passing between sort of, let's say, string diagrams and these more classical presentations. And I think your question is quite fascinating, because I think that gives us some things to think about, how to get this additional logical structure on this in this kind of, let's say, more algebraic way, or
because eventually you end up also thinking about the affine relations, which again are very logical in spirit, right? So kind of, there might be something nice to be said there. I don't know, but I certainly am interested. But thank you. That's very helpful.
Thank you for the question.
Okay, well, let's thank Pawel again. So thanks again.
Okay, thanks a lot. Thanks. It's been a pleasure.
Yep. Okay. Thank you. Bye.
Bye, everyone.